After studying this module, you shall be able to determine the total surface area of an adsorbent, know about multilayer adsorption and BET adsorption isotherm, know how BET equation explains various adsorption isotherms, know how to determine the thermodynamic parameters of adsorption process. First, we shall have a look at the determination of surface area of adsorbent. We know that the volume occupied by 1 mole of an ideal gas is equal to 22.414 decimeter cube, or the number of molecules occupying 22.414 decimeter cube volume is equal to the Avogadro's number, which is equal to 6.023 into 10 to the power 23. Therefore, the number of molecules n corresponding to V mono will be given by V mono by 22.414 into 6.023 into 10 to the power 23 as our equation 1. The total surface area of the adsorbent can be obtained if we multiply the above number n by the area of cross section of a single molecule. A. The latter can be obtained from the density measurements. Assuming close packing with negligible volume, the volume V occupied by a single molecule can be obtained from the density ρ as follows. Rho is equal to m divided by V into Na as given by equation 2, where Na is the Avogadro constant 6.023 into 10 to the power 23, or V equals to m divided by rho into Na as our equation 3. If the molecule is assumed to be spherical with radius r, then V will be given by 4 by 3 pi r cube, which can be written as equal to m by rho times Na as shown in equation 4. Or we can find the value of r as given by r equals to 3 by 4 pi into m divided by rho into Na whole raised to the power 1 by 3 as shown in equation 5. Now, A will be given by A equals to pi r square, which can be written as 3 by 4 pi into m divided by rho into Na raised to power 2 by 3 as shown in equation 6. However, the area of cross section obtained from the relation 6 is not accurate. This is because we have made use of the following approximations. Number 1, we have assumed a close packing since we do not have the data on the exact nature of packing of the adsorbate molecules on the surface of the adsorbent. Number 2, the void volume is neglected. Number 3, the adsorbate molecules are assumed to be perfectly spherical with no distortions. The results can be significantly improved if we have detailed knowledge about the crystal structure. Emmet and Brunner made use of the following approximation to calculate the area of cross section of a single molecule. The average cross section of the adsorbate molecules is the same as that of the molecules in the corresponding plane of closest packing in the solidified gas. That is, A is given by 4 into 0.86 into 1 by 4 root 2 into m divided by rho times Na to the power 2 by 3 as shown in equation 7. Once the value of area of cross section of the single molecule is obtained, the total surface area of the adsorbent is given by A times n as our equation 8. Now we shall study about the multilayer adsorption. In the Langmuir adsorption, a monolayer formation of adsorbate gas molecules on the surface of the adsorbent is assumed at low pressure and moderately high temperatures. This assumption, however, is not valid at high temperatures and low pressures. When the gas pressure is high, greater number of adsorbate molecules strike unit area of the adsorbent in unit time. And when the temperatures are low, the thermal energies of the gas molecules are low, insufficient to overcome the van der Waals forces of attraction between the adsorbed molecules and the surrounding unadsorbed molecules. As a result of these two effects, the solid adsorbent holds on many layers of gas molecules onto its surface, resulting into what is called as the multilayer adsorption. Multilayer adsorption is especially prevalent at gas pressures close to gas saturation pressure at a particular temperature. Therefore, what we observe is not only type 1 adsorption isotherms, but also type 2, 3, 4 and 5 adsorption isotherms. One of the most successful theories to explain the multilayer adsorption is the BET adsorption isotherm. Now we shall study the BET adsorption isotherm. In 1938, Brunner, Emmett and Teller gave the true picture of adsorption as being multilayer in nature. The various postulates of the theory proposed by them, called as the BET theory, are as follows. Number 1. The adsorption involves the formation of multilayer of adsorbent molecules on the surface of solid adsorbent, unlike in the Langmuir adsorption, whereby only unimolecular layer formation takes place. The multilayer adsorption takes place in manner. Vapor plus free surface of adsorbent gives rise to single complex. Vapor plus single complex gives rise to double complex. Vapor plus double complex gives rise to triple complex, and so on till the multilayer formation. Number 2. The Langmuir concept of fixed number of adsorption sites being available onto the surface of solid adsorbent applies to each layer. Number 3. The interactions between the adsorbent molecules in the adsorbed layer are neglected. Number 4. For the formation of single complexes, the assumptions made by Langmuir model still hold true. Number 5. The concept of dynamic equilibrium adopted by Langmuir model holds true in each layer. That is, the rate of desorption from the first layer is equal to the rate of adsorption in the preceding layer. Number 6. The forces that produce condensation are responsible for binding energy in the successive layers. Number 7. The heat of adsorption in the first layer is constant. After the formation of the first layer, the heat of adsorption is assumed to be equal to the latent heat of condensation of vapors. Now we shall talk about the derivation of BET adsorption isotherm. On the basis of the postulates, Brunner, Emmett and Teller derived the BET equation. We represent the formation of multilayer of gas molecules on the adsorbent surface with the help of following equilibrium equations, as shown in equation 9, as M plus S gives rise to Ms, M plus Ms gives rise to M2S, M plus M2S gives rise to M3S, and so on up till M plus M n minus 1s gives Mns, where M is the unadsorbed gas molecule, S is the active site on the adsorbent surface, Ms is the single complex formed, M2 is a double complex formed, and so on. The equilibrium constants for the equilibrium reactions can be written as shown by equation 10, as K1 equals to Ms divided by M into S, K2 equals to M2S divided by M into Ms, K3 equals to M3S divided by M into M2S, and so on. Now, the concentration of M is directly proportional to the pressure of the gas P, and the concentration of S is directly proportional to the fraction of freely available adsorbent surface theta naught. Ms is proportional to the fraction of the adsorbent surface having unimolecular coverage theta 1. M2S is directly proportional to the fraction of the adsorbent surface having bimolecular coverage theta 2, and so on. Substituting for above proportionalities in equation 10, we get K1 equals to theta 1 by P theta naught, K2 equals to theta 2 by P theta 1, K3 equals to theta 3 by P theta 2, and so on, as shown in equation 11. The value of K1 is usually very large as compared to other equilibrium constants. This is due to the fact that with the increase in the distance from the adsorbent surface, the interaction between the gas molecules and the solid adsorbent decreases. Therefore, the constants K2, K3, K4, etc., although with different numerical values, will be much smaller than the constant K1. In other words, the difference between these equilibrium constants will be much smaller as compared to the difference between K1 and K2. Therefore, we can have the assumption as K2 is approximately equals to K3 is approximately equals to K4 is approximately equals to KL, as shown in equation 12. where Kl is the equilibrium constant corresponding to the saturated vapor-liquid equilibrium given as saturated vapor in equilibrium with the liquid, and Kl will be equals to 1 by P naught as shown by equation 13. Using the approximation from equation 12, the various equilibria in equation 11 can be written as K1 equals to theta 1 by P theta 1, K2 approximately equals to Kl equals to theta 2 by P theta 1, K3 approximately equals to Kl is equal to theta 3 by P theta 2, and so on as shown in equations 14. Rearranging the expressions and making use of equation 13, we get the equations as shown in 15. If we assume that the entire adsorbent surface is covered, then the total coverage of the first layer will be given by theta total equals to theta naught plus theta 1 plus theta 2 up till so on equals to 1 as shown in equation 16. Substituting the equations 15 in equation 16, we get the equations 17. Since P by P naught is less than equal to 1, the expression within the curly brackets of equation can be written as 1 plus P by P naught plus P by P naught square plus equals to 1 minus P by P naught raised to power minus 1 equals to 1 upon 1 minus P by P naught as shown in equation 18. Substituting equation 18 in equation 17, we get theta total is equals to theta naught into 1 plus K1P divided by 1 minus P by P naught equals to 1, or theta naught is given by the expression shown in equation 19 equals to 1 minus P by P naught divided by 1 plus K1P minus P by P naught. The total volume of the adsorbed gas corrected to STP, that is a standard temperature pressure, is given by V total equals to V mono into theta 1 plus 2 theta 2 plus 3 theta 3 plus so on as shown in equation 20, where V mono is the volume required for the monolayer adsorption. Substituting the values of theta 1, theta 2, theta 3 and so on from equation 15, we get V total equals to V mono into K1P theta naught into 1 plus twice P by P naught plus thrice P by P naught raised to power square plus so on as shown in equation 21. The expression within the bracket of the above equation 21 is a derivative of the expression within the curly brackets of equation 17. Thus, in view of equation 18, we get 1 plus twice P by P naught plus 3 times P by P naught square plus so on is equal to 1 upon 1 minus P by P naught square as equation 22. Substituting equation 22 in equation 21, we get V total equals to V mono into K1 P theta naught divided by 1 minus P by P naught square as our equation 23. Substituting the value of theta naught from equation 19, we get V total equals to V mono into K1P divided by 1 minus P by P naught into 1 plus K1P minus P by P naught as our equation 24. The pressure P in the above equation 24 may be replaced in terms of relative pressure P by P naught as shown. P equals to P naught into P by P naught, which can be written as 1 by KL times P by P naught as shown in equation 25. The substitution of equation 25 in equation 24 gives equation 26 as shown. The ratio of K1 by KL is designated as constant C. Therefore, we get the equation 27 as V total equals to V mono into C into P by P naught divided by 1 minus P by P naught into 1 plus C P by P naught minus P by P naught. Equation 27 is the required BET equation for multilayer adsorption of gas molecules on the adsorbent surface. Equation 27 can be written as P by V total into P by P naught equals to 1 upon V mono C plus C minus 1 upon V mono C into P by P naught as shown in equation 28, where V total is the volume of gas adsorbed under given conditions of temperature and pressure reduced to standard conditions. B mono is the volume of gas required to form monolayer on the adsorbent surface reduced to standard conditions. C is the characteristic constant for a particular adsorbent system. The validity of the BET adsorption isotherm can be proved by plotting a graph between P upon V total into P naught by P and P by P naught as shown in figure, which shows the BET adsorption isotherm. A straight line plot with slope C minus 1 divided by C into V mono and intercept equals to 1 upon V mono C validates the BET adsorption isotherm. The two constants V mono and C can be therefore evaluated. After V mono is known, the surface area of the adsorbent can also be evaluated as discussed. The plot between P by V total into P naught minus P and P by P naught gives a straight line till the gas pressure is less than 1/3 of the gas saturation pressure. It is observed that at high pressures, deviations are obtained. Now, we shall see the physical significance of constant C. The relation between the standard free energy change for adsorption delta G naught and the adsorption equilibrium constant K1 naught can be written as delta G naught equals to delta H naught minus T delta S naught equals to minus RT ln K1 naught. Therefore, ln K1 naught is equals to delta S by R minus delta H naught by RT, or K1 naught equals to exponential of delta S naught of adsorption divided by R minus delta H naught adsorption divided by RT, or K1 naught can be given by equation 29 as equal to exponential delta S adsorption by R into exponential minus delta H naught adsorption by RT, where delta S naught adsorption and delta H naught adsorption are the standard entropy and standard enthalpy change for adsorption respectively for monolayer formation of gas molecules on the adsorbent surface. Or we can write that K1 naught is equals to G1 into exponential of minus delta H naught adsorption divided by RT, which can be written as also equals to G1 into exponential of delta H1 of desorption by RT, where G1 is the entropy factor and delta H1 naught desorption is the standard enthalpy for desorption for monolayer formation of gas molecules on the adsorbent surface. We can write the similar equations for equilibrium constant KL as follows. KL naught is equals to GL into exponential of minus delta HL naught condensation by RT, which can be further written as GL into exponential of delta HL naught of vaporization by RT, where GL is the entropy factor and delta HL naught of condensation is the standard enthalpy change for condensation of gas molecules on adsorbent surface, and delta HL naught of vaporization is the standard enthalpy change for vaporization of liquid adsorbed on the adsorbent surface. The ratio between these two equilibrium constant gives the constant C in the BET equation as C equals to K1 naught by KL naught equals to G1 exponential minus delta H1 naught of adsorption by RT divided by GL into exponential of minus delta HL naught of condensation by RT, which can be further written as equal to G1 exponential delta H1 naught of desorption by RT divided by GL into exponential of delta HL naught vaporization by RT, or the C can be written as exponential of delta H1 desorption minus delta HL naught of vaporization by RT. In simple terms, C can be thought to be as written as exponential of E1 minus EL by RT, where E1 is the enthalpy of adsorption of gas in the first layer and EL is the enthalpy of condensation of the gas. E1 minus EL is the net heat of adsorption. Now we shall see the explanation of different types of adsorption isotherms. We have the following BET equation as P by V total into P naught minus P equals to 1 upon V mono C plus C minus 1 by CV mono into P by P naught as given by equation 28. Multiplying the equation 28 throughout by P naught, we get equation 29. Now C is equals to K1 by KL and KL equals to 1 by P naught. Or we can say that C is equals to K1 P naught or K1 is equals to C by P naught. Equation 30. Substituting this value of K1 equals to C by P naught from equation 30 in the above equation 29, we get equation 31 as P by P V total into P naught divided by P naught minus P equals to 1 upon V mono K1 plus C minus 1 by C V mono into P. If we assume C is much greater than 1 and P naught is much greater than P, then the equation 31 gets modified to P by V total equals to 1 upon V mono into K1 plus P by V mono, which is the Langmuir equation. Thus, under the assumptions of C being very much greater than 1 and P naught being very much greater than P, the BET equation can be reduced to the Langmuir adsorption equation. Under these circumstances, BET equation can satisfactorily explain the monolayer adsorption as in type 1 adsorption isotherm. Type 2 adsorption isotherm is observed when C is greater than 1, that is, delta H1 of desorption is greater than delta HL0 of vaporization. Here, the monolayer formation starts, it gets completed, and then the multilayer formation starts. Type 3 adsorption isotherm can be explained by the condition C is less than 1, that is, delta H1 naught of desorption is less than delta HL naught of vaporization. Here, the multilayer formation starts even before the monolayer formation is complete. Type 4 adsorption isotherm, which is a duplicate of type 2 adsorption isotherm, can again be explained by the conditions that delta H1 naught of desorption is greater than delta HL naught of vaporization. In this, the adsorption reaches a saturation value much before the gas saturation pressure is attained. This is explained by the fact that in addition to the multilayer formation is taking place on the adsorbent surface, adsorption also takes place in the capillary pores, cracks and crevices of the adsorbent. In type 5 adsorption isotherm, the lower portion of the isotherm matches with that of type 3 adsorption isotherm. Therefore, this can be explained by the condition that delta H1 naught of desorption is less than delta HL naught of vaporization. The isotherm at higher pressure matches with type 4 isotherm, again indicating that the adsorption reaches a saturation value much before the gas saturation pressure is attained. This can be explained by the fact that capillary condensation takes place in addition to the multilayer formation on the adsorbent surface. Now, we shall talk about the limitations of BET isotherm. Although BET adsorption isotherm can successfully explain the different types of adsorption isotherms, yet it is associated with following limitations. Number 1. BET equation holds good when the ratio P by P naught lies between 0.05 to 0.35. Out of this range, deviations from linearity set in. Number 2. An inherent assumption of BET isotherm is that the gas adsorbate has liquid properties. However, this is true only when the critical temperature is high. But permanent gases like hydrogen, oxygen, nitrogen, etc. have low critical temperatures. Now, we shall see the determination of thermodynamic parameters of adsorption process. We can derive the relations for change in enthalpy, entropy and free energy of adsorption process as follows. From the Langmuir equation, we have K1 equals to theta upon 1 minus theta into 1 by P as equation 32. In this equation, the equilibrium constant K1 is a function of temperature only. The temperature dependence of K1 can be obtained by the Van 't Hoff equation as d by dt of ln K1 equals to delta H naught of adsorption divided by RT square as shown in equation 33. From equation 32, we get at constant theta, K1P will be constant, or ln K1 plus ln P is equals to constant. Differentiating this equation with respect to T at constant theta and using equation 33, we get d by dt of ln K1 is equals to d by dt of ln P by P naught. We can write this as d by dt of ln P by P naught equals to minus delta H naught of adsorption by RT square, or d of ln P by P naught is equals to minus H naught adsorption by RT square times dt. Integrating, we get ln P by P naught equals to delta H naught of adsorption by RT plus constant, as equations 34 and 35. A plot between ln P by P naught versus 1 by T gives a straight line with a negative slope equals to delta H naught by R, as shown in figure shows the plot between ln P by P naught versus 1 by T. The value of delta H obtained from the slope of the graph is called the isoteric enthalpy of adsorption. Integrating equation 34 within limits, we get dP by P from limits P1 to P2 equals to minus delta H by R into 1 by T squared dt, integral from limits T1 to T2. Solving, we get equation 36 as ln P2 by P1 gives delta H adsorption by R into 1 by T2 minus 1 by T1. The change in free energy and entropy of adsorption can be calculated from the relations as follows. Delta G of adsorption equals to minus RT ln K1 naught, and delta S naught of adsorption is equals to delta H naught adsorption minus delta G naught adsorption by T. These are equations 37. Now we shall summarize what we have learned in this module. Total surface area of the adsorbent can be obtained if we multiply the number of molecules corresponding to V mono by the area of cross-section of a single molecule. Brunner, Emmett and Teller gave the true picture of adsorption as being multilayer in nature. BET adsorption isotherm is based on certain postulates which give the BET equation as P by V total into P naught minus P equals to 1 by V mono C plus C minus 1 by CV mono into P by P naught. BET adsorption equation can successfully explain type 1, 2, 3, 4 and 5 adsorption isotherms. However, it is associated with certain limitations. The thermodynamic parameters of adsorption processes can be determined using the following relations. ln P2 by P1 equals to delta H by R into 1 by T2 minus 1 by T1. Delta G naught of adsorption is equals to minus RT ln K1 naught, and delta S naught of adsorption is equals to delta H of adsorption minus delta G naught of adsorption by T.